Hello students, welcome again to Lectures Club, and today I will explain JFET parameters and characteristics. The contents of today's lecture are the drain characteristic curve, and using the drain characteristic curves we will define different terms like ohmic region, active region and the breakdown regions of JFET, and we will also define some other terms like pinch off voltage of JFET, IDSS and the cutoff voltage of JFET. If you remember, in the previous lecture we briefly discussed on the working of JFET. If you didn't watch my lecture, I recommend you kindly watch my lecture before watching this lecture, so you will have a better understanding of different terms of JFET or different parameters of JFET. I will put the link of the video in the description box, as well as you can see the link here, so you can directly go by clicking here. If you remember that in the previous lecture we discussed that there are two conditions are necessary for the working of JFET. One condition was when gate to source voltage is 0, and one condition was when gate to source or voltage lesser than 0. Actually, proper working of JFET depends upon this condition, but this condition is also necessary to define different terms. But here we will use these two conditions in parallel to define some terms which are, or define different parameters which are necessary to understand the working of JFET. In this condition, you can observe here that VGS is equal to 0. It means that gate to source voltage is 0, and we applied variable voltage between the drain and the source. And similarly, here we applied negative voltage at the gate and static voltage between the drain and the source. And when we change this voltage, what will happen? The depletion region will vary. Depletion region between this p-type material as well as depletion region between the n-type body of the JFET. Same will happen here. The dotted lines actually these are representing the depletion region. Similarly, when we change this drain to source voltage, the depletion region will also vary, and ultimately the variation in the depletion region will put an impact on the drain current or the current flowing through the JFET in both conditions. So we will use the change in drain current and the change in change in drain current as well as the change in voltage, or in other words, we will change the drain to source voltage and the current will change, and we will have different parameters which are necessary for the working to understand the working of JFET. So let's start our today's lecture. So when we will change drain to source voltage, the drain current will change because the depletion region between the gate and the drain will vary, as well as depletion region between the gate and the source will also vary, because the change in the potential difference is taking place. You can see here the drain is connected to the 5 volt and the source is connected to 0 volt, as well as the gate is also 0 volt. So when we will change drain to source voltage, the potential difference between the drain and the gate is higher, and so the depletion region will further widen towards the drain, and depletion region will be lower between the gate and the source. When depletion region will increase, depletion region of the right side as well as depletion region of the left side, when depletion region will increase, the width of the channel is basically between these two p layers. Electrons will flow between these two p layers. When depletion region will increase, definitely the path for the flow of electron will be decreased. When path for the flow of electron or the channel for the flow of electron will decrease, then definitely it will impact upon the drain current. Similarly, if this depletion region decreases, as well as what happens, definitely this current through the channel will increase because depletion region is decreasing. So when we are changing the drain to source voltage, drain current is changing. We are using these two things to define different terms which are necessary to understand the working of JFET. So here you can see that on the horizontal axis we will plot drain to source voltage, and on the vertical axis we will plot the drain current. Let's say initially we started increasing the drain to source voltage from 0. When we increase the drain to source voltage from 0, the current will also increase, because in this situation the depletion region is not wider enough to put an impact on the flow of current, or the resistance of the channel is almost constant. I repeat, when we will start when we'll start changing the drain to source voltage, what will happen? The drain current will increase. When drain current will increase, because the width of the channel is very large, or the resistance of the channel is almost constant, and depletion region is not large enough to put an impact on the width of the channel or put an impact on the flow of electrons. So current will increase. When you increase the voltage, current will increase, and this behavior is linear. You can observe the straight line is, this blue straight line is representing the linear behavior of JFET. But with this will not happen all the time. It will happen to some extent, and this is called the ohmic region. You remember Ohm's law says that if the resistance and some conditions are constant, when you change the voltage or you increase the voltage, current increases. When you decrease the voltage, current decreases. So here you can observe, when you increase the voltage, current increases, and when you decrease the voltage, current decreases. So up to this point the JFET is in the ohmic region. But after that, when you keeps on increasing drain to source voltage, this depletion region definitely will increase, because the potential difference between the drain and the source is increasing. Gate, it means gate is a p-type material, made of p-type material. Gate is a lower potential, and drain is made of n-type material, and drain would be at high potential. So the depletion region will be increased in the reversed bias condition. So when you further keeps on increasing the drain to source voltage, this depletion region will increase, and this will definitely ultimately it will put an impact on the width of the channel, and the width of the channel will continuously keeps on decreasing. When when the depletion region is increasing, the width of the channel is decreasing. So a point will reach when you further increase the drain to source voltage, the drain current will not increase, or it will become constant, because these two regions have become so close to each other. These two depletion regions or depletion layers become so close to each other, or have come so close to each other. So you further increase the drain to source voltage, the drain current will not increase, and the drain current will become almost constant, because the channel has become narrower or very small. The width of the channel has become very small, and the current is constant. So current will not increase, because when current will increase, more electrons wants to move through the channel, but channel has become narrower, so no more electrons can flow through the channel, and a particular number of electrons will flow through the channel, and current will become constant. Now the JFET has entered into active region. In the active region, the JFET, the current through the JFET is constant, or in other words you can say the JFET has gone into saturation mode. So in active region, when you increase the drain to source voltage, current will not increase, current will constant. So the voltage, the value of the voltage, I mean the value of the drain to source voltage at which the current has become maximum and is not changing further, this voltage is called pinch off voltage. I repeat, the value of drain to source voltage at which the current through the JFET has become constant and maximum as well, this is called the pinch off voltage. Okay, I mean the current will be maximum at the pinch off voltage and will not change further. If you further increase the drain to source voltage, current is not increasing and has become constant. This is called the active region. But after active region, if you further keeps on increasing the drain to source voltage, a point will reach when this depletion region will collapse, and when this depletion region will collapse, what will happen? The JFET will be damaged, or a very huge amount of current will be passed through the JFET, or JFET will damage. So what is IDSS? IDSS is the maximum current, and it is defined as drain to source current with gate shorted. It means that IDSS is always measured when the gate to source voltage is 0. This IDSS is always given in the data sheet of JFET. This IDSS is the maximum current of JFET and is measured when VGS is equal to 0. And another thing is, this IDSS is always given in the data sheet of JFET. Now only the one term remains, that is cutoff voltage, and we will use this condition when we will apply the negative voltage at the gate to define the cutoff voltage. Here you can observe that we applied negative voltage at the gate and positive 5 volt at the drain, or between the drain and the source. So when there is no voltage at the gate, maximum drain current will pass through the through the JFET. And when you will increase this negative voltage, let's say now the gate is at -1. So when the gate will be at -1, what will happen? The potential difference between the drain and the gate will increase. Before that, potential difference was 5 minus 0, 5 volt. Now the potential difference is around 6 volt. 5 minus into -1 is equal to 6 volt. Now depletion region will widen, more widen as compared to the gate at the 0 volt. Now the potential difference will increase, further increase. If you further increase the voltage, the gate to source voltage, depletion region will further increase and keeps on. If you keeps on increasing the voltage, depletion region is increasing because the potential difference between the drain and the gate is increasing, and drain current is decreasing. You can observe that when you increase the gate to source voltage, what happens? The drain current decreases. This straight line representing the different values of drain current. This is the value of the drain current at VGS -1, and this is the value of drain current at VGS -2, and this is the value of drain current at VGS is equal to -3. Because when the depletion region increases, the channel width decreases, and as well as the amount of flow of drain current also decreases. And then we further increase the voltage up to -4, and drain current further decreases, and then a point reaches when what happens? Actually, these depletion regions completely block the flow of current. Now that JFET is not working and no current is flowing through the JFET. At this point the voltage is called the cutoff voltage, and you can observe that the cutoff voltage is always opposite to the drain to source voltage. If drain to source voltage is 6 volt, cutoff voltage would be -5. If drain to source voltage is 6 volt, cutoff voltage would be -6 volt. If drain to source voltage is 3 volt, cutoff voltage is equal to -3 volt. And it is opposite in case of P channel MOSFET. Now another important thing you can observe that at every voltage, gate to source voltage, there is a pinch off taking place. You should not mix this pinch off with pinch off voltage. At the pinch off voltage, maximum drain current passes through the JFET. But here if you increase the voltage beyond the pinch off voltage, definitely drain current is increasing. So this is not a pinch off voltage, this is not a pinch off voltage, these are pinch off points basically. But what is a pinch off voltage? When the maximum drain current passes through the transistor, and pinch off voltage is when VGS equal to 0. So hopefully you have understood the entire working of JFET as well as the parameters and characteristic curves of JFET. You must subscribe the channel. I request you subscribe the channel, so I will come up with more videos. Hopefully the next video would be on the transconductance of JFET. And do not forget to turn on the notification button, and you will be notified when I will upload the video on transconductance of JFET. Thank you so much. Bye bye. Stay blessed.